Okay, so we left off at looking at maps of functions and noticing that making the arrows go the other direction is how you represent the inverse function. So is this a function? Yes, it's clear that each state has a population number associated with it. And then is it one-to-one? And it is, because none of the population numbers for these states is the same. So now let's make some pricing functions and say if I have each item has one price, that's fine for being a function. But then if I have one price that corresponds to two different items, then my function is not one-to-one. If your function, if your relation is not even a function, so if I have an item that doesn't have a price, this is not even a function, so then you don't even need to ask the second question. If somebody says, is this a one-to-one function? The answer is, it's not even a function. So it's a two-part question. Is this a one-to-one function? You first decide, is it a function? And then, is it one-to-one? Okay, so the next way of representing a function that we looked at was ordered pairs. So if you have a set of ordered pairs, x comma y, then the inverse function is going to be the set of ordered pairs that you get by writing the coordinates of each point in the opposite order. The domain becomes the range, and the range becomes the domain. So in this function, the domain is the list of x values. So it's a discrete list. It's not an interval or a group of continuous numbers of x values. It's discrete 5 different x values. So then that is going to be the range of the inverse function. So this is if we're talking about the inverse function. So then the range of the function is 1, 3, 0, -4, -8, the y values that we see. So that is the domain of the inverse function. So the answer to the question of what is the inverse of this function? It's these ordered pairs with their coordinates reversed. But do you see how that's not going to change anything for the point 33 or the ordered pair 0, 0? But then we'll have -4, 2 and -8, 7. And notice that I'm calling them ordered pairs because they aren't necessarily representing points on a graph. They could represent lots of different things. They're just a set of ordered pairs that we often do represent on a graph. Okay, so this is a picture similar to the one I drew earlier, where you have a domain of f and a range of f. I wanted to talk about something on this picture where even if the domain of f is a bunch of numbers, it's possible that these numbers represent weights, and that even if the range of f is a bunch of numbers, maybe they represent height. And so if the f function says, if I know your weight, I can model your height, and the f inverse function says, if I know your height, I can model your weight. So even though they're all numbers, they're very different kinds of numbers. The numbers in the pink blob could be pounds, and the numbers in the blue blob could be inches. Okay, so be careful. This symbolic language, f with a -1 superscript, is symbolic for the inverse function of f. And if you want to write with an argument, you read this f inverse of x. So the language goes in the order of the symbols as you read left to right. F inverse of x. So this -1 is not an exponent. even though it's in the position of an exponent, it's doing a completely different job and has a completely different meaning. So it does not mean the reciprocal of f. If you wanted to write the reciprocal of f, you would have to put the f of x in a bracket with an exponent of -1 to mean 1 over f of x. Okay, so the order of the notation is important. It makes a big difference. If you're writing in French, the accents mean different things, and you can accidentally say the wrong thing by doing the accents incorrectly. So math language is just as important and just as dependent upon doing the symbolic language correctly to have the right meaning. Okay, verifying inverse functions. This is a way you can decide if two functions are indeed inverses of each other. So if you apply the function first and then the inverse function, you will get back to the x value you started with. So again, let's make a picture. If I have the domain and the range, and here is the x value I started from, and the f function gets applied, the thing I land on is called f of x. Well, if I then apply the f inverse function, I will get right back to where I started at x. Notice that this x is in the domain of f. So don't get hung up on that it's the letter x. That's just a symbol that's saying this place I started. So let me draw another picture of the second math sentence. This says start at some value in the range and apply the inverse function first. So we're using the letter x again, but think of my example where this could be weight and this might be height. So this guy you land on is f inverse of x, which if you then apply f to, you will end up back at x, but this x is in the domain of f inverse, also known as the range of f. So notice they're coming from different buckets of numbers, even though they're all numbers. Okay, so here's some examples where your task is to verify that these two functions given are inverses of each other. So the question is g the same as f inverse? And you test that by doing what we were just looking at, and you compose the two functions and see if indeed you get back to the x that you started with. So this would be one of the many reasons we studied composition of functions not that long ago. So if I write f of g of x, that tells me that everywhere there was an x in the original function, I now want to insert g of x. And then I'm going to do the algebra that's indicated here and get x plus 8 minus 8. Sure enough, that equals x, so we're halfway there. So now we need to show also that g of f of x will get us back to x. So g says take whatever the input is, divide that by 4, and add 2. And the input now is f of x. So 4x over 4 is x, negative 8 over 4 is minus 2, and then plus 2. And so we got to x. And so we already knew the answer was going to be yes, because it just says verify. It doesn't say, is this the same? But the answer is yes. The g function that's given is indeed the inverse of f, because we've just showed that it behaves as f inverse would need to behave. Okay, so the second example is a little trickier. So let's go through that one where I want to do f of g of x first. So everywhere I see an x in the f function, I'm going to put a big empty space with parentheses and say everywhere I see those empty parentheses, I'm going to put g. Oh my gosh, it's a complex fraction. No wonder we needed to remember how to do these. So remember there's two different ways of doing these. Either simplify numerator, simplify denominator, and then divide. Or my strong preference is the multiply by the cleverly chosen version of 1 that does the simplifying kind of all in one step. So I need to distribute this 1 minus 2x to the first term and the second term. And then the 1 minus 2x in the denominator, distribute to the first term and the second term. So when I distribute the 1 minus 2x in the numerator, I'm going to cancel with that first denominator and get 3x plus 5. And then going to have minus 5 times 1 minus 2x over, again, the denominator will cancel when I do the first distribute. Then I'll have plus 3 times 1 minus 2x. So now it's just a matter of doing a bunch of algebra. 3x plus 5 minus 5 plus 10x over 6x plus 10 plus 3 minus 6x. So this looks like 13x over 13, which is x. We're halfway there. So I'm going to let you do the other part because you know what the answer has to be. But it was really good practice of simplifying a complex fraction to do the g of f of x and see if you can get it to also come out as x. So when a function is presented as a graph, this is the easiest form for finding the inverse function because every ordered pair a comma b that's a point on the graph will become the point b comma a to be a point on the graph of the inverse function. So the blue function is f and the pink one is f inverse. So every point a comma b maps to the point b comma a, and you can see visually that the effect is you reflect the graph of f about the line y equals x. So there's a lot of words that get used for how you reflect. People say in, on, over, about, all of those are fine. But it is important that you use the word reflect. Don't use some other language like flip or rotate. Those are not correct. It needs to be the word reflect. Okay, so let's see how we would draw the graph of the inverse function. If the point 1, 2 is on the graph of f, then the point 2, 1 is going to be on the graph of f inverse. 0, 1 is on the graph of f, so 1, 0 is on the graph of f inverse. Negative 1, 0 is instead going to be 0, negative 1. And then the points in f were connected with a straight line, so the points in f inverse will also be connected with a straight line because the transformation of reflecting is a rigid transformation. It does not change the shape of the graph. And then let's think about the point negative 2, negative 2. What that's telling us is that f of negative 2 is negative 2. Well, that means also that f inverse of negative 2 is also negative 2. So that point doesn't go anywhere, but it is also a point on the graph of f inverse. So pretty straightforward. Okay, so up till now, I've just been giving you functions and saying, here, is this the inverse? But I didn't say how did I find them. So this last bit is the procedure for given a function, find its inverse. Okay, so it's step by step. It's called an algorithm that you just go step by step, do it the same way every time. You got it. So the first step is instead of writing f of x, I write y, just because f of x is 4 characters and y is 1. So it's going to save me a lot of writing. So then, because of the way the inverse function works, every y is going to become an x, and every x is going to become a y. And then we need to solve for y. If what you're trying to solve for is in a denominator, don't think very hard about step 1. Step 1 needs to be multiply both sides by the denominator because you can never solve for something that's in the denominator. So on the left, I'm going to have xy plus 4x, and on the right, the denominator cancels. That was the whole point. So I'll have equals 2y minus 3. And then I need to get everything that has a y on one side and everything that doesn't have a y on the other side. So I'm going to keep the y's on the left. So I'm going to subtract 2y from each side and have xy minus 2y plus 4x equals negative 3. And then I'm going to subtract the 4x from both sides so that I have only terms with y on the left and everything else on the right. Then this is a point where students often get stuck. You have 2 copies of y, but to solve for y, you need 1 copy of y. So the trick here is to factor out the y. So you just need to do enough of these where that is what your intuition tells you to do. And then we're going to divide both sides by x minus 2. And then you're going to label your answer f inverse of x equals negative 4x minus 3 over x minus 2. And there's lots of variations on this. If you decided to have all the y's on the right-hand side, yours might look a little different. If you didn't put your negative 4x and your minus 3 in the same order as I did, yours might look a little different. But it should be the equivalent. If you multiply the top and the bottom by negative 1, you can usually get yours to look like somebody else's. So make sure and do lots of these for practice. This is a really important skill that I will definitely test you on. And then here's a little summary. If you like having summaries and you want to put this in your notes, that would be a good idea. So make sure and ask if you have any questions.